Bismillahirrahmanirrahim. Assalamu alaikum students. Today my topic is the electric potential electric potential of continuous charge distributions. This is our topic for today. In the last lecture, we derived the expression for the electric potential due to a point charge, which was V equal to 1 by 4 pi epsilon naught Q by R, in which it was assumed that the potential at R tending to infinity is 0, that is V is 0 if R tends to infinity. Then if we have many point charges, for that we we can use superposition principle. Potential due to many point charges V1 plus V2 plus V3 plus so on. There are n charges up to Vn. We use superposition principle of field as well, but in case of potential it is easier to sum these numbers because potential is a scalar quantity, right? Now today we talk of electric potential of continuous charge distributions, and you know in continuous charge distributions charge can be distributed in one dimension. So in one dimension we define a quantity lambda, which is called linear charge density. In two dimensions, if charge is distributed in two dimensions, then we define a quantity sigma, surface charge density. And in three dimensions, we define a quantity rho, which is volume charge density, right? Now I will give you a simple example, that is a ring of charge. So example here which we discuss is uniformly charged a ring of charge, right? So let me draw the figure. Consider this ring of charge. Right? Let me use some other color. So this ring has some center. So we place a ring in the xy plane, right? This is the direction. O is the origin of coordinate system, and that is also the center of this ring, right? Let there be positive charge on the ring. So it is positively charged ring of charge. It is placed in xy plane. Origin coincides with the center. Now we select a point P along its central axis, z distance from the center of the ring. Now we want to find the potential at point P. Where is point P located? It is z distance from the plane of the ring along its central axis, right? Let Q be the total charge on the ring. Lambda, linear charge density, is assumed to be constant. And let R, capital R, be the radius of the ring. So R is radius of the ring, right? What is the procedure? We select an element of the ring which has charge dq, which is little r distance from point P, right? So let dV be the electric potential at point P due to dq. That means this portion of the ring. We can assume that, or you can use point charge expression for this. So dV is 1 by 4 pi epsilon naught dq by r. Simple. We have assumed that it is a point charge and made use of this expression. Charge contained in the element is dq and distance of point P from the element is r, right? If V is the potential at point P due to ring, then from superposition principle, we have, remember, in continuous charge distributions, superposition principle, when we use, this sum becomes an integral, right? So V is simply integral dV, and dV itself is 1 by 4 pi epsilon naught dq by r. Now see, for all elements making of the ring, this distance of the point from the element is same from the symmetry of the problem, so it can be taken outside the integral. That means it will simply become 1 by 4 pi epsilon naught r integral dq, right? Integral dq is just total charge in the ring. So my expression is 1 by 4 pi epsilon naught q by r, because integral dq is so V is 1 by 4 pi epsilon naught q by r. Don't confuse it with the point charge expression. Here q is the total charge on the ring and r is distance of this element or any other element of the ring from point P. We want it in terms of the distance of the point from the center and radius. Now this is here a right angular triangle. So we can make use of Pythagoras theorem and write. So I can write from figure, let me name it figure 1. Figure 1, r square is capital R square plus Z square. Simple Pythagoras theorem. Hypotenuse square is base square plus perpendicular square. So R is square root R square plus Z square. Therefore, V, let me name it first, this second. So using second in first, right? Do we have any other equation? No. V turns out to be 1 by 4 pi epsilon naught q by under root r square plus z square. This is our required expression. So I encircle it, right? R square plus z square. So if we have a uniformly charged ring and we take a point p z distance from the plane of the ring along its central axis, and capital R is the radius of the ring, q is the total charge on the ring, then the potential is given by this expression 1 by 4 pi epsilon naught q by square root of r square plus z square. Let us move to next topic. Our next topic is equipotential surfaces. You know it. I will just remind you. See, we know if we have a charge, any charge, where we are taking point charge, now surrounding it in the space, there exists this electric field, right? Now that electric field can be represented in scalar terms by potential, we know. Now electric field can be expressed mathematically, potential can be expressed mathematically, as we have done, for example, in case of a ring of charge. This is the expression for the potential. E can be also expressed graphically by the use of lines of force. We draw electric lines of force surrounding the charge, and that graphical representation is in consistency with the mathematical equations. We frame the rules for drawing lines of force that way. Similarly, we can represent potential graphically. Now, that graphical representation of potential involves the construction of equipotential surfaces. Here we have, in case of E, we have lines of force which graphically represent electric field surrounding a charge. In case of potential, we talk of equipotential surfaces. Now what we do when we have an electric field in certain space, we construct or draw, a family of surfaces, connecting points, family of surfaces by connecting, let me make it clear, surfaces by connecting points having the same value of the electric potential, right? So we construct or draw a family of surfaces by connecting points having the same value of electric potential. Now these surfaces are called equipotential surface. These surfaces are called equipotential surfaces. They are called equipotential surfaces. Now, the shape of equipotential surfaces depends on the kind of electric field. For example, take uniform electric field. So we construct the electric lines of force for uniform electric field. It is uniform E electric field. Everywhere field strength is same and direction is also same to the right. So, for example, this is in 3 dimensions, and this figure is showing the cross section of that figure with the plane of the board. So if you take, for example, this line perpendicular to the electric lines of force, I can show you that at all points on this line, potential is same. See, I take 2 points. This is my point A, this is my point B. You know, VB minus VA is minus WAB by Q naught. So if you have to find the potential difference between these 2 points, you have to take test charge, move it from point A to point B, calculate the work done by the field and substitute in this expression. Now see, if you move the test charge from A to B, displacement vector will be upward, electric field is to the right, so force will be to the right because test charge is positive. Angle between force and displacement will be 90 degree, so work will be 0. WAB will be 0. That will mean VB is equal to 0. That means electric potential at point A and point B is same, right? This cos 90 is 0. That is true for all points on this line. And if we extend this line to 3 dimensions, it is a planar surface. So it's an equipotential surface. A planar surface. This planar surface. On all points of the surface, potential is same. So it is an equipotential surface. Equipotential surface. Similarly, if you draw another line or surface like this, it is also an equipotential surface. This is also an equipotential surface. This is also an equipotential surface. So conclusion is, for uniform electric field, the equipotential surfaces are planes equally spaced, right? You know, the strength of the field in case of electric lines of force is represented by density of lines. Same is true with equipotential surface. If the density of equipotential surfaces is constant, is same throughout, then field is uniform. So for uniform electric field, equipotential surfaces are planes equally spaced, and these planes are perpendicular to lines of force always. So I write perpendicular to lines of force. Now consider point charge field. Point charge field. You see, it is non-uniform. Non-uniform. So it is my point charge. Now how we draw electric lines of force. Electric lines of force are like this, radially outward. Density is varying. As you move outward, density becomes less, field strength becomes less. You know electric field, electric potential due to point charge is 1 by 4 pi epsilon naught q by r. So if I connect those points which are equidistant from the charge and join them, I will get an equipotential surface. So equipotential surfaces one be roughly like this, and you can construct another one. Remember, these are actually spheres centered on the charge, and this diagram shows cross section of those. So conclusion is, for a point charge, the equipotential surfaces for a point charge, the equipotential surfaces are spheres concentric, spheres centered on the charge, right? For a point charge, the equipotential surface are spheres centered on the charge. Let me write here. So these are equipotential surfaces. I have constructed two, you can construct many, right? One more thing, it is non-uniform field, so they will not be equally spaced. When we construct these equipotential surfaces, what we do, we keep the potential difference between two consecutive surfaces constant. If you do this in case of point charge, you will see that as you go away from the charge, density of the equipotential surfaces will decrease, indicating field strength is decreasing. Now, more complicated charge distributions have more complicated shapes of equipotential surfaces, but one thing is always true, that no two equipotential surface can intersect, right? And equipotential surfaces are always perpendicular to lines of force, because every equipotential surface will have a value of potential. So I write here equipotential surfaces are always perpendicular to electric lines of force, always perpendicular to electric lines of force. Another thing I said, no two no two equipotential surfaces can intersect or cross, right? Another thing, let me move to next page. Suppose I construct three equipotential surface. Let the potential for this surface is VA, the surface A, the surface B, and the surface C, its potential is VC. Now, if we move along this surface, let me use another color from this point to this point along path 1. Then I show another path. Let this be path 2. Let this be path 3. And let this be path 4. C. Work done by the electric field for path 1 W1 is 0. Why? Because points which are connected by path 1 lie on the same equipotential surface. So VB and VA are same. Work done by the field is 0. But remember, always if you move on equipotential surface along any path, if your initial and final point is lying on the same equipotential surface, work done is 0. Same is true for second path. Even if path is not lying wholly on the surface, but since initial and final point lie on the same surface, work done by the field is 0. What about W3 and W4? They both are not equal to 0. Why? Because the points connected by path 3 and path 4 lie on different equipotential surfaces. There will be some work done by the field as we move along these paths. They are non-zero. They are equal also. Why? Because they are connecting to same equipotential surfaces. So work done by the electric field for path 3 and path 4 is same. So you must keep these things in mind when you consider handling or constructing equipotential surfaces. Now we move to the next topic. Remember, we have discussed how to calculate potential from the field. We have already discussed how to calculate electric potential from the electric field, right? We showed VB minus VA is EL if the electric field is uniform and we select 2 points A and B L distance apart in the field along the field, right? We also showed for non-uniform field VB minus VA is minus A to B E dot ds, and we said the potential is the line integral of electric field. And in this expression, both points A and B were assumed to be within the field. Then we said if point A is taken at infinity and at infinity potential is taken as 0, then VP, that is potential at any point in the field, is written by this integral, this equation. VP, potential at any point within the field E, is minus integral infinity to point P E dot ds, right? Now we want a reverse of this. That means how to calculate electric field from the potential. How to calculate electric field if electric potential is given. It is evident from this there must be involvement of derivative, because if potential is integral of field, field must be derivative of potential. So we want to show that. So I write calculating the field from the potential. Calculating the field from the potential. Right? So what we do, consider two equipotential surfaces differing in potential by dV. Right? So these are my two equipotential surfaces, right? Let there be some direction S. I define some direction S. Direction S. Right? What I do next, I take a test charge Q naught, move this test charge from one surface to the next surface through displacement ds. Right? Starting at point P on surface 1. Now at point P, when I move it, there is an electric field existing in the space, and at point P, electric field must be perpendicular to the surface there, so it will be somewhat like this. Right? So theta is the angle between electric field and displacement vector. I want to calculate the work done by the field as I move the test charge from one surface to other surface along direction S. Right? So what is that? We know this expression VB minus VA is equal to minus WAB by Q naught. So this is my dV now. This is my work I represent by dW, which is being done on test charge. So I can write dW is minus Q naught dV. dW is minus Q naught dV. I name it first because the two equipotential surfaces across which I am moving my test charge are differing in potential by amount dV, right? So also I can calculate the same work by another way. Work done by the electric field is by definition F dot ds. F is the force on the test charge, which is Q naught E. So I can write Q naught E dot ds. My angle between, I can evaluate this dot product. I can write Q dot E ds cos theta. Because theta is the angle between field and this displacement vector. It's Q naught E ds cos theta. Now I can equate these two. So this is the work done by the field. This is the same work. So I can equate. Right? Combining first and second, we get. So what I get? Minus Q naught V dv minus q naught dv is equal to what? Q naught e ds cos theta, right? Q naught e ds cos theta. So Q naught will go, I will get what? E is, or E cos theta is minus d by ds. I name it equation third. I got E cos theta is minus dv by ds. Or I write it this way: E subscript s is minus dv by ds, where es, which is E cos theta, is component of E along s direction, right? Because E is making angle theta with s direction, so its projection in s along s direction or on s direction is E cos theta, which in vector terminology we name or call E component of E along s direction. So component of E along s direction is Es, which is minus dv by ds, right? I name it 4. So if I state this equation 4 in words, what does it say? It says the negative of the rate of change, negative of the rate of change of the potential with position in any direction, is the component of electric field E in that direction. Remember it. S direction was arbitrary. It is saying actually the negative of the rate of change of potential in S direction is the component of electric field in S direction. So since S direction is arbitrary, we can generalize it to any direction and say the negative of the rate of change of the potential with position in any direction is the component of E in that direction. And remember, this minus is indicating that the field points in this minus indicates that field points in the direction of decreasing V. E points in the direction of decreasing V. In the direction of decreasing V. Now there will be one direction. There will be one direction ds for which the quantity minus dv by ds is a maximum. There will be one direction ds for which the quantity minus dv by ds is a maximum. right? And from equation 4, we see that ES will also be maximum for this direction and will in fact be E itself, right? E is minus dV by ds max, and in it 5. So if you find in general minus dV by ds, that will give you the component of E and that particular direction, S direction. But if you find its maximum value, that will give you the maximum value of ES, and that maximum value will be the total field, right? Now this maximum value of dV by ds at a given point, so write the maximum value of dV by ds at a given point. A given point is called the potential gradient at that point, right? Potential gradient at that point. Now the direction ds for which dV by ds has a maximum value is always at right angles to the equipotential surface, corresponding to the direction of electric field, right? Now, if we take the direction ds, now if we take the direction ds to be in the directions of x, y, and z axis, we can find the 3 components of E, 3 components of electric field E at any point from equation 4, this one, from equation 4, right? It's simple. Component of electric field along x direction will be minus dou v by dou x. Component of electric field along y direction is minus dou v by dou y. Component of electric field along z direction is minus dou v by dou z. You know what it means? That means we name it 6. You know what it means? It means if you are given a potential as function of position x, y, z, you partially differentiated x, negative times of that gives you x component of field. You differentiate the given potential function with y, negative times that gives you y component of the field, and you differentiate the potential partially with z, negative times of that gives you the Z component of the electric field, right? So this was our today's topic. I give you the homework now. So homework. Let me use next page for homework. Question 1. Calculate the potential at a point on the axis of a circular plastic disc of radius capital R, one surface of which carries a uniform charge density sigma. I repeat the question. Calculate the potential at a point on the axis of a circular plastic disc of radius capital R, one surface of which carries a uniform charge density sigma. Question 2. Three charges of plus 122, let me write it clearly, plus 122 millicoulomb each are placed on the corners of an equilateral triangle 1.72 meter on a side. If energy is supplied at the rate of at 831 watts, how many days would be required to move one of the charges onto the midpoint of the line joining the other two. I repeat the question. Three charges of plus 122 millicoulomb each are placed on the corners of an equilateral triangle 1.72 meter on a side. If energy is supplied at the rate of 831 watt, how many days would be required to move one of the charges onto the midpoint of the line joining the other two? This is all for today. Do your homework. Don't waste your time. Go through all the video lectures which I have shared with you. And don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.